It consumed a man's worth of risk every 20 minutes. That is what the workers said, in their own way, in 1893. They wipe a man out here every little while, not every year, not every month, every little while. A chain breaks, a ladle tips, the iron explodes. Picture a vessel taller than a two-story house, shaped like an egg standing on its end, filled with 30 tons of liquid metal at nearly 3,000 degrees. Enough liquid metal, poured all at once, to bury a city bus. Now picture men standing close enough to touch it, watching its mouth for the exact shade of orange that tells them whether they live through the next 10 minutes or don't. That vessel was called a Bessemer converter. The factories built to house it were some of the most profitable structures ever raised on American soil. And the same machine that built railroads, skyscrapers, and a nation's industrial spine also built something else. A permanent, rotating cast of men standing directly beneath tons of molten iron, with nothing between them and disaster but a fire's color and a foreman's nerve. This is the story of why that factory had to exist, why the machine inside it had to be violent by design, not by accident, and why the same engineering decisions that made America's steel cheap also made its steelworkers, for decades, into targets. We're going to find out exactly how that happened, and what it cost the men standing closest to the flame. The beast that made steel cheap. Before this machine, making steel was an act of patience. A skilled craftsman called a puddler stood over a furnace for hours, stirring molten iron by hand, slowly burning off impurities with heat and sweat and decades of trained instinct. One man, one furnace, 1 ton of usable iron in a full day's labor, if the weather and his back cooperated. It was a trade passed down like a family recipe, and it kept the price of steel high enough that most of the world still built with iron, or with nothing at all. A puddler's son learned the trade from his father, who'd learned it from his own father before him, and that slow inheritance of skill was the only bottleneck standing between the world and the steel age. No amount of money could shortcut it. You couldn't hire your way around a shortage of trained hands. You had to grow them, one apprenticeship at a time, and the planet was industrializing far faster than that could ever keep pace. That was the impossible problem. The world wanted steel. Bridges wanted steel. Railroads, the new arteries of an industrializing planet, wanted steel by the hundreds of thousands of tons. But there weren't enough puddlers alive to make it, and there never would be. You couldn't train your way out of this bottleneck. You needed to blow the door off the entire process. Here's what that actually took. Fact 1. Before 1856, making 50 pounds of usable steel could take an entire month of skilled labor. 50 pounds. About what one grown man weighs in armor. Fact 2. The man who solved it wasn't trying to build bridges or railroads at all. Henry Bessemer was trying to build a better cannon, because the Crimean War kept producing artillery barrels that shattered under their own gunpowder, sometimes killing the gun crews before the enemy got the chance. Fact 3. His solution sounded insane to every expert who heard it. Blow cold air directly into molten iron. His own foundry workers warned him it would simply freeze the metal solid. They were wrong, and the reason they were wrong is the reason this story turns dangerous. Fact 4. When Bessemer first tried it, in his own backyard workshop, the vessel didn't just heat up, it erupted. Flames and molten slag shot skyward. Sparks rained onto the rooftops of nearby buildings, and nobody could get close enough to shut off the air supply. He'd built, in his own words, a veritable volcano in a state of active eruption. 10 minutes later, it stopped. He had his steel. He also had a process that would never again behave gently. Fact 5. He wasn't even the only one. An American ironmaster named William Kelly had stumbled onto the exact same trick a few years earlier, blowing air through molten iron at his own furnace in Kentucky. Word got around that Kelly had lost his mind, and his own business partners reportedly tried to have him committed to an asylum rather than fund what looked like lunacy. He lost the patent fight, and history gave the credit, and the name, to Bessemer instead. Fact 6. The math behind this machine is almost impossible to believe. A single converter could turn 10 to 20 tons of raw iron into usable steel in 20 minutes flat. The old method needed a full day of backbreaking labor to produce a single ton, 20 minutes versus 24 hours, with the new method moving 20 times the material. That ratio alone is the entire reason every iron baron on the planet started building converters the moment they heard the numbers. Fact 7. Bessemer's own son later calculated just how much money this machine eventually generated. He worked out that the world's annual production of Bessemer steel, converted into solid gold, would form a column 5 feet wide and over 109 feet tall. More gold than 3 straight years of every gold mine on Earth combined could produce. Fact 8. And this is the one that should make you nervous. The first American test of this machine happened in Troy, New York, in 1865, and it worked exactly as violently as Bessemer's backyard experiment. Witnesses watched the egg-shaped vessel erupt in fire, on command, on schedule, every single time. That wasn't a malfunction. That was the machine working perfectly. And a perfectly working Bessemer converter was, by design, a controlled explosion that human beings were about to start standing next to for a living, 12 hours at a time. Fact 9. The steel this machine produced wasn't just cheaper, it was dramatically better, and the proof showed up under real-world load. A rail made from puddled iron typically lasted about 2 years under traffic before it had to be replaced. A Bessemer steel rail lasted roughly 10, while carrying nearly 9 times the weight per car that the old iron rails could handle. Cheaper, faster, and stronger, all from the same 20-minute eruption. Fact 10. Not everyone trusted it right away. When New York City began planning the Brooklyn Bridge, engineers fought bitterly over whether to use the new Bessemer steel at all, with one prominent voice in the project arguing in writing against trusting the cheaper, faster metal with the lives of everyone who'd eventually cross that bridge. The argument wasn't really about quality. It was about trusting a process that, by its own inventor's account, behaved like an erupting volcano every single time it ran correctly. One last fact before we move past the invention itself. Bessemer's converter didn't just outproduce the old method, it nearly erased it within a single generation. In the late 1860s, American factories were turning out less than 3,000 tons of Bessemer steel rail a year, a rounding error next to the iron rails still dominating the market. By the mid-1880s, iron rail production had all but vanished, replaced by well over 1 million tons of Bessemer steel rail annually, selling at a fraction of the old price. An entire established industry, with its own skilled trade and its own century of tradition, was functionally wiped out in about 15 years by a machine that worked by erupting. Word of Troy's success reached a young Scottish-American businessman touring Europe in the summer of 1872, watching Bessemer rails being made cheaply overseas. His name was Andrew Carnegie, and what he saw convinced him to rush home and build something bigger than Troy had ever attempted. Bigger, and therefore more violent, because in this machine, scale and danger always climbed the same staircase together. But size brings its own problems. A converter that processes 20 tons in 20 minutes generates 20 tons worth of fury in that same window. The bigger the vessel, the bigger the eruption. Carnegie wasn't just buying a faster way to make steel. He was buying a machine that, the larger it got, became correspondingly more dangerous to everyone standing nearby, and he was about to build the largest version anyone in America had yet attempted. The factory he financed would change Pittsburgh forever. But first, his engineers needed to understand exactly what kind of monster they were building inside it. Because the violence Bessemer described in his own backyard experiment wasn't a problem waiting to be solved. It was baked into the physics of the entire process, and that meant every man who'd ever worked near one of these vessels was inheriting a danger nobody had figured out how to remove. They'd built the beast. Now came the hard part, making it work, day after day, without it eventually killing the men who ran it. 20 minutes inside a volcano. Here is the chain reaction, stripped down to its bones. Molten pig iron gets poured into an egg-shaped vessel, roughly 20 feet tall, about the height of a 2-story building standing on end. Air gets forced through holes at the bottom, called tuyères. The oxygen in that air reacts violently with the silicon, manganese, and carbon dissolved in the iron. Those reactions don't just burn off impurities, they generate enough heat on their own to keep 30 tons of metal liquid without burning a single piece of coal. No external fuel. The iron, quite literally, cooks itself clean. But could fire and air alone really refine raw iron into something strong enough to hold up a railroad bridge? The chemistry says yes, and it happens fast. As the temperature climbs past 1600 degrees Celsius, flames up to 30 feet tall, taller than the vessel itself, shoot from the converter's mouth with what one observer called eye-searing intensity. The entire vessel rocks gently on its mountings as the reaction churns inside it, the roar loud enough to drown out shouted commands from 10 feet away. Workers learned to read the flame the way sailors read weather. Its color and shape told them, second by second, how close the blow was to finished. There was no gauge. There was no digital readout. There was a man, standing as close as he had to, staring directly into 30 tons of barely contained chemical violence, deciding by eye alone when to shut the air off. That decision mattered enormously. Stop too early, and you'd left dangerous impurities in the steel. Stop too late, and you'd burned out too much carbon, leaving the metal brittle and useless, the kind of steel that shattered cannons instead of strengthening them. The entire blow lasted roughly 20 minutes from start to finish. 20 minutes to get it exactly right, with no instant replay and no second attempt on that batch. Get it wrong, and 30 tons of effort and material was wasted, or worse, became structurally unreliable steel that someone, somewhere, would eventually trust with their life. So why build the vessel egg-shaped in the first place? Why not something simpler? Because the egg shape was a direct answer to the violence inside it. Engineers needed enormous headroom above the liquid metal so that the spitting, erupting slag had somewhere to go besides directly into a worker's face. The vessel's narrow waist and wide chamber gave the reaction room to vent upward, away from the operators, at least in theory. Even the converter's offset mouth, the spout, where flame and slag escaped, was a deliberate compromise between letting the volcano breathe and keeping its discharge pointed somewhere survivable. Every dimension of that machine was a negotiation with an explosion that nobody had figured out how to prevent. They could only decide which direction it would go. That single design decision tells you everything about this entire technology. The engineers weren't trying to make the converter safe. They were trying to make its violence predictable enough to survive standing next to. The vessel itself was mounted on trunnions, like a cannon barrel, so it could tilt to receive its molten charge, swing upright for the blow, then tilt again to pour finished steel into ladles. That tilting mechanism had to handle enormous stress, because nothing about 30 tons of liquid metal moves gently. A misaligned trunnion, a worn gear, a cable under too much load. Any one of those failures meant a converter full of molten steel could shift unpredictably while crews worked beneath it. But chemistry created its own trap, and it split the steel world into winners and losers almost overnight. Bessemer's original process worked beautifully on low phosphorus iron ore, the kind found in select deposits in England and, fortunately for Carnegie, in parts of America. Feed it ore with too much phosphorus, and the resulting steel turned brittle, useless for rails or beams. For years, this limited where Bessemer steel could be made at all. Continental Europe, sitting on enormous reserves of high phosphorus ore, watched the Bessemer revolution from the sidelines, unable to use the very process that was making American and British steel barons rich. The fix came from an unlikely source, a young chemist named Sidney Gilchrist Thomas, working largely alone and outside the major steel companies, identified that swapping the converter's interior lining from acidic clay to a basic material like burned limestone or dolomite allowed phosphorus to be drawn into the slag instead of ruining the steel. It was a brilliant solution, and it opened up the vast phosphorus-rich ore deposits of France and Germany to mass steel production for the first time, eventually making basic Bessemer steel the dominant method across continental Europe for decades. It was also, in its own way, a trap for the men who worked there, because the basic lining produced even more slag than before, more molten waste material that had to be handled, drained, and disposed of by hand near the same furious heat that created it. Solve one problem with this machine, and you almost always created more work for the men standing closest to it. There's one more piece of chemistry essential to understanding why this machine demanded human nerve at every step. After the blow finished and nearly all the carbon had burned out of the iron, the metal wasn't yet steel. It was nearly pure iron, far too soft and brittle to use. A metallurgist named Robert Mouchet solved this by developing Spiegeleisen, a carbon and manganese alloy that workers stirred back into the converter in carefully measured amounts. Too little, and the steel stayed soft. Too much, and it turned brittle enough to shatter under load. The exact failure that had started this entire chase for better metal in the first place. Without Mouchet's contribution, Bessemer's earlier steel batches were notoriously unpredictable, sometimes excellent, sometimes worthless, with no reliable way to tell which you'd get until it failed in the field. Now stack these realities on top of each other. A vessel filled with molten metal at temperatures that could vaporize flesh in an instant. No way to monitor the reaction except watching its flame by eye. A tilting mechanism under constant mechanical stress. A lining that, however well engineered, demanded that someone physically handle the slag it produced. And a chemical finishing step that required workers to add alloy to a vessel that was, by definition, still actively erupting. And underneath all of that sat one more daily nightmare nobody could engineer away. The converter's bottom, the detachable plate fitted with the air holes, simply wore out. The intense heat and constant chemical assault degraded it faster than almost any other part of the machine, and a worn bottom didn't fail gently. It failed by letting molten metal break through where it shouldn't, sometimes with almost no warning. For years, replacing a failed bottom meant shutting the entire converter down and letting 30 tons of refractory brick and steel cool from nearly 3,000 degrees before anyone could touch it. A process that could swallow most of a working day and bleed profit straight out of the plant. Captain Jones would later solve part of this problem at Edgar Thomson with his swappable bottom design, letting crews change it out without a full cool-down. But solving the production problem didn't eliminate the danger underneath it. It just meant the danger now happened faster and more often, because the plant could afford to run the converter harder than ever before. This is what made Carnegie's new plant, when it finally rose along the Monongahela River, more than just a financial gamble. It was an experiment in whether American workers and American engineering could run this volcano continuously, day after day, without it eventually erupting on the wrong person. The men who built that plant believed they could manage the danger. What they hadn't yet discovered was exactly how, and exactly how often, the danger would manage them instead. On paper, the design was elegant. A self-sustaining chemical reaction, no fuel required, finished steel in 20 minutes. Keeping that elegant design running on a factory floor, with tired men and worn equipment, would prove to be an entirely different kind of engineering problem. The men who stood beneath it. Carnegie's new works rose at Braddock, Pennsylvania, on the site of an old colonial battlefield, where General Edward Braddock had been mortally wounded more than a century before British soldiers ever imagined steel mills replacing muskets. Construction broke ground on January 1, 1873, designed by the same Alexander Hawley who'd built Troy, on 107 acres of land secured along the Monongahela River. The project nearly collapsed before it began. A financial panic that same year froze credit across the entire country, halting construction for 10 days until the partners managed to float a $200,000 bond issue just to keep workers on the payroll. Carnegie hired a master mechanic named William Jones to oversee construction and operation. A Welsh-American Civil War veteran everyone called Captain Jones, who'd already helped build Bessemer converting works back at Cambria Iron in Johnstown, and who brought roughly 200 of his most trusted men with him when he left. On August 22, 1875, the converter at Edgar Thomson Steel Works produced its first heat of liquid steel, destined to become 2,000 rails for the Pennsylvania Railroad. Within a year, the plant had turned out more than 32,000 tons of steel rail. Captain Jones improved the design further, inventing a converter bottom that could be swapped out without cooling the entire vessel, a fix that kept the plant running almost continuously instead of losing hours to every routine repair. Production climbed to 225 tons of rail per day. But who actually worked that floor? Who stood beneath 30 tons of liquid metal, shift after shift, for $10 a week? Mostly immigrants. Welsh, German, Irish, and later Eastern European laborers, many fresh off the boat, drawn by jobs that required no prior skill in steelmaking, only strength and the willingness to show up. That was the entire point of the Bessemer process. It had broken the puddlers' monopoly on skilled labor, and it meant the men who replaced them needed no apprenticeship at all. They needed something else instead: the nerve to stand close to fire that periodically exploded, and the stamina to do it for 12 hours straight, 7 days a week, with a single yearly holiday on the 4th of July. A typical crew worked in rotating roles around the converter: men who tipped molten pig iron into the vessel, men who monitored the blow itself, men who handled the slag pouring off as waste, and men who worked the crane that swung massive ladles beneath the converter's mouth to catch the finished steel. Every single one of those jobs put a human body within range of something that could kill in an instant if a mechanism failed or a calculation went wrong by even a few seconds. Workers at mills across the region had their own names for the most dangerous stations on the floor. The platform directly beneath a converter mid-blow was sometimes simply called the pit, and the men assigned there for a shift knew exactly why nobody wanted that posting twice in a row. The heat alone was its own kind of violence. Standing near an active blow meant working in temperatures that could approach the temperature of an oven set to clean itself, except this oven was open, roaring, and throwing sparks across an entire factory floor. Men worked in short rotations near the worst of it, ducking back to recover before returning, because nobody's body could absorb that kind of heat continuously for an entire shift without collapsing. Workers described their faces yellow where the light struck them and violet in shadow, standing in a glow that turned ordinary men into figures from a painting of hell. The noise alone, described as a fluttering, humming roar that silenced everything else, meant shouted warnings could be lost entirely in the din, swallowed by a machine that didn't care whether you'd heard the danger coming. How long could a man actually last in that kind of heat, shift after shift? Not particularly long, according to the men who lived it. A sociologist who studied the industry in this era called "What Happened to Steelworkers" old age at 40. The long hours, the physical strain, and the constant temperature swings between roaring heat and outdoor cold simply used men up faster than ordinary labor ever did. Men in their 30s carried the stooped backs and weathered faces of laborers twice their age, and crews regularly lost members not to dramatic accidents, but to the slow accumulation of damage that 12-hour shifts inflicted year after year, and that was before anything went catastrophically wrong. Consider the average worker's compensation against that toll, roughly $10 a week, just above what counted as the poverty line in 1890. It took the combined wages of nearly 4,000 steelworkers to match what Andrew Carnegie personally earned in the same period. The men closest to the converter, the ones in the pit, breathing slag fumes and dodging spatter, were among the lowest-paid workers in the entire operation, despite standing in the single most dangerous spot on the property. Risk and reward, in this particular factory, moved in exactly opposite directions. One worker, interviewed in 1893, described the rhythm of disaster with the kind of weary precision that only comes from having lived inside it. They wipe a man out here every little while. Sometimes a chain breaks, and a ladle tips over, and the iron explodes. Sometimes the slag falls on the workman. Of course, if everything is working all smooth and a man watches out, why, all right, but you take it after they've been on duty 12 hours without sleep, and running like hell, everybody tired and loggy, and it's a different story. That single quote contains the entire design flaw of the era's steel industry. The technology demanded constant human vigilance, under conditions specifically engineered to erode vigilance. 12-hour shifts, round-the-clock production schedules, exhausted men working beside molten metal that offered no margin whatsoever for a half-second of slowed reaction time. For Andrew Carnegie, efficiency mattered more than safety, and his mills stayed perpetually the most productive in the world, precisely because he tore out and replaced equipment the instant something faster became available. Investments he recouped quickly through reduced labor costs, while the human cost of running his machines harder rarely showed up on any ledger he kept. For months, sometimes years, plants like Edgar Thomson ran without catastrophe. The crews learned the rhythms of their converter, learned which sounds meant normal operation and which meant trouble brewing. They developed an almost superstitious respect for the machine, the way sailors respect the sea. But respect doesn't repeal physics, and the men who ran this floor every day were about to discover exactly what happened when 12 straight hours of exhaustion met 30 tons of molten metal that had never once, in its entire violent history, been forgiving of human error. When the chain broke. Small failures came first, the way they always do. A chain showing wear, replaced just in time. A ladle that tipped slightly off balance, spilling a manageable amount of slag instead of a catastrophic amount. A bottom on the converter wearing thin faster than expected, caught during a routine check instead of mid-blow. These near misses rarely made the newspapers. They were simply the background noise of an industry that ran on thin margins between functioning and disaster. But the warnings were there for anyone paying attention. Small things, things the operators noticed and reported up the chain. Workers across the steel-making regions of Pennsylvania and Ohio described boiler and furnace explosions occurring almost regularly enough to lose count, claiming laborers to poisonous gas, falling cinder, and sudden bursts of molten metal that gave no warning before they happened. One observer studying conditions in the Mahoning Valley's mills called the work simply terrific and horrible, and meant it literally, not as exaggeration, but as the plainest available description of what happened when these machines failed. The question was always whether management acted on the warnings before the next failure became the kind nobody walked away from. Those were the small failures, the ones absorbed quietly into the daily rhythm of the floor. But every steel district eventually produced a failure too large to absorb quietly, the one that made headlines, the one that put a name and a face on a danger most people preferred to think about only in the abstract. Edgar Thomson's came on September 26, 1889, and it didn't strike a nameless laborer. It struck the most famous steelman in the country, Captain Bill Jones, the engineering brilliance behind Edgar Thomson's rise to the most productive steel mill on earth, was on the floor with his workers that day, trying to personally clear a furnace jam. It was exactly the kind of hands-on intervention that had made him beloved by every man who worked under him. He never asked his crews to do anything he wouldn't do himself, and after the catastrophic Johnstown flood that same year, he'd shut the entire plant down on his own authority and led 300 of his own workers to help with the relief effort in his old hometown. The furnace gave way under pressure. A section of superheated cinder and metal, suspended 7 feet above the workers' heads, tore loose and poured down onto the group below. One man was killed instantly. Another died of his injuries days later. Jones, trying to escape the falling cinder, was thrown backward, striking his head against the iron edge of a cinder car as flame and burning material rained around him. His face and hands were severely burned. A nearby employee managed to shut off the blast, finally choking off the flames, but by then the damage was already done. Newspapers initially reported that Jones would likely recover. His burns, while serious, didn't appear life-threatening at first. But could anyone really survive the kind of trauma that came with being thrown into burning cinder and striking solid iron head first? Within days, Jones's condition worsened. He developed concussion symptoms, then slipped into semi-consciousness. He died at the homeopathic hospital in Pittsburgh on the night of September 28, 1889, 2 days after the accident. The man who had personally engineered more safety-conscious innovations into Edgar Thomson than perhaps anyone else in American steelmaking, killed by the same family of hazard he'd spent 14 years trying to tame. This is the part the machine's success story rarely mentions. The man most responsible for proving American Bessemer steel could be made cheaply, reliably, and at staggering scale, died exactly the way the floor workers under him sometimes did. Caught beneath superheated material, with no warning and no way to escape in time. If the engineering genius who understood this technology better than almost anyone alive couldn't outrun it, what chance did an exhausted 12-hour shift laborer have? Jones's death wasn't an isolated tragedy. It was a single visible data point in a pattern researchers would later try to quantify with brutal precision. In the 1880s, fatal accidents in steel mills accounted for roughly 1 in every 5 male deaths across the entire city of Pittsburgh. Not 1 in 5 workplace deaths, 1 in 5 deaths of any kind, among men, in an entire major American city. Steelmaking itself had become one of the leading causes of death for the men who lived there. A landmark investigation, known as the Pittsburgh Survey, conducted in 1907 and 1908, tracked industrial deaths across an entire year in the region and documented 526 fatalities. Investigators went case by case, tracking the cause of each death, who was blamed, and what it cost the families left behind. Of the families who lost someone, more than half received $100 or less in compensation from the company that employed them, often less than 2 months of the wages the man had been earning when he died. There was no workplace safety regulation with teeth. There was no OSHA, no mandated inspection regime, no legal requirement that companies do anything beyond what cost efficiency already demanded of them. The cost of human life simply hadn't yet been built into the economics of cheap steel. Decades later, immigrant laborers at some mills were still being killed or injured at roughly double the rate of English-speaking workers, stuck disproportionately with the dirtiest and most hazardous stations on the floor, the same stations near the converter and the furnace mouth that had claimed Captain Jones. What did the public make of all this? Newspapers covered individual disasters when they were dramatic enough. Explosions, multiple deaths in a single incident, anything with a vivid enough story to sell papers. Captain Jones's death, given his fame, ran in papers well beyond Pittsburgh, and for a few days, the broader country glimpsed what mill towns already knew intimately. But there was no sustained outrage, no broad political movement demanding the industry slow down or spend money on protection. The country wanted cheap rails, cheap bridges, cheap skyscraper frames, and steel kept getting cheaper, precisely because companies weren't required to spend on the safety of the men producing it. A dead steel worker, however tragic, didn't slow a single order moving through the mill. That equation would eventually provoke its own kind of reckoning, though not over safety directly. In 1892, just 3 years after Jones's death, workers at Carnegie's Homestead plant, including men who'd transferred from Edgar Thomson in solidarity, struck over a different grievance entirely. Wage cuts imposed while the company's most dangerous machines kept demanding the same brutal physical toll as ever. Carnegie's partner, Henry Clay Frick, fired the entire workforce of 3,800 men, built a barbed wire fence around the plant, and brought in 300 armed Pinkerton guards to protect strikebreakers. The resulting battle killed at least 10 people and wounded hundreds more, a different kind of violence than the converter floor produced, but one rooted in the same underlying truth. The men who ran these machines were treated as replaceable, and replaceable men rarely get listened to until they make themselves impossible to ignore. The governor eventually sent state troops to end the standoff, and Carnegie quietly rebuilt his workforce with non-union labor in the strike's aftermath. Wages fell, the hours stayed exactly the same. The dead were buried, the plants kept running. Production never meaningfully slowed because of any single accident, no matter how prominent the victim. But something had shifted in how the public understood these factories. Not enough to force reform overnight, but enough that the romantic image of the heroic steel baron taming nature with brute machinery had picked up a permanent shadow. Beneath every ton of cheap steel sat an unspoken ledger of burned hands, lost eyes, and men who simply never came home from a 12-hour shift. And the machine that had made it all possible was about to face an entirely different kind of threat. Not an explosion, but obsolescence, as a quieter, less violent process began stealing away the very advantage that had made the Bessemer converter unstoppable in the first place. The volcano that went quiet. By the late 1880s, the very efficiency that had made the Bessemer converter revolutionary was starting to work against it. The process that finished a heat of steel in 20 minutes was also too fast for careful chemical control. There simply wasn't time, in that violent 20-minute window, to test and adjust the metal's composition with any real precision. For rails and basic structural steel, that hardly mattered. But as American industry demanded steel for more specialized purposes, armor plate, precision machinery, eventually automobiles, the Bessemer converter's signature speed, the very trait that had made it unbeatable, became its fatal limitation. The machine that had won the race by being fast was about to lose the next one for exactly the same reason. The open hearth furnace offered the opposite trade. Slower, yes, taking hours instead of minutes, but allowing operators to sample the molten steel repeatedly, adjusting its composition with a precision the violent Bessemer blow could never match. By 1890, at Carnegie's own Homestead Works, 16 open hearth furnaces were running continuously, each one producing 40 tons of steel every 6 hours, using waste gases from the molten iron itself to generate temperatures approaching 3,000 degrees. It was, in its own way, just as demanding and dangerous as the converter it was slowly replacing. One worker in 1919 described running toward a 100-ton ladle of white-hot steel to hurl a sack of coal into it, as hot a job as can be imagined. But it gave companies the precision the market increasingly demanded. What replaced the Bessemer converter, in other words, wasn't safety, it was better chemistry. By the turn of the century, most of Carnegie's steel came from these open hearth furnaces instead of the violent egg-shaped vessels that had built his empire. The Bessemer process became functionally obsolete for most commercial steelmaking by the 1930s. The very last Bessemer converter operating in North America finally went dark sometime in the 1960s, ending a century-long run that had started with a single small experiment, exploding sparks onto an English roof. But here's something most people never realize. The volcano never fully died. According to multiple historical accounts, one Bessemer shop reportedly continued operating into recent decades in the Ural Mountains of Russia, the very last working descendant of the machine Henry Bessemer built in his own backyard more than a century and a half ago, still occasionally erupting in that same furious 20-minute eruption of fire and slag that terrified onlookers in 1856. What does remain, far more visibly, is the world this machine built. Every bridge, every early skyscraper frame, every mile of railroad track laid across America between roughly 1870 and 1900 likely traces its existence back to a converter just like Edgar Thomson's, blowing air through molten iron in 20-minute bursts of controlled violence. The price of steel rail dropped from $100 a ton to $50 a ton in just 2 years after Carnegie's plant opened. A collapse in cost that made railroads, bridges, and buildings affordable on a scale the puddling furnace could never have supported. Cities grew because steel got cheap. Steel got cheap because a machine erupted like a small volcano every 20 minutes, and men stood close enough to manage that eruption by hand. By 1890, American steel mills were running virtually around the clock to keep pace with railroad demand alone. More than 50,000 miles of new track laid in a single decade, each mile representing a small multiple of converter blows that someone, somewhere, had stood close enough to watch. That's the part of the story that the gleaming photographs of finished bridges and skyscrapers leave out. The Edgar Thomson plant where Captain Jones died still operates today, more than a century and a half after its first heat of steel, though its dangers have been engineered down considerably by modern standards. Automated controls, mandatory protective equipment, safety regulations with actual legal force behind them, all things that simply didn't exist for the men who worked there in 1875. There were no sensors to detect a failing converter bottom back then. There was no automatic shutoff if a chain showed too much wear. The only safety system most of these men had was their own trained instinct, and instinct, no matter how sharp, eventually loses to exhaustion, to chance, to 30 tons of metal that doesn't care how many years of experience you've accumulated. So why does this story matter, beyond its dates and tonnage figures? Because every cheap steel beam holding up a modern building carries an invisible debt to men whose names mostly went unrecorded, men who stood beneath an erupting vessel of molten iron for $10 a week, who watched flame color instead of digital gauges, who knew that "they wipe a man out here every little while" wasn't an exaggeration, but a simple operating fact of their job. The factory that built Bessemer converters didn't just manufacture steel. It manufactured a particular kind of American sacrifice, anonymous, repeated, and almost entirely unrecorded outside a handful of newspaper columns and one grim labor survey counting 526 dead men in a single year. Visit the few surviving artifacts of this era today, and the danger has been sanitized into something almost decorative. A retired converter sits motionless behind glass in a museum somewhere, its egg-shaped hull cold and silent, looking more like a sculpture than the volcano it once was. Visitors walk past it without breaking stride, never imagining the noise, the heat, or the men who once stood close enough to read its flame for a living. That silence is its own kind of monument. It says nothing about the chains that broke, or the bottoms that wore thin, or the 12-hour shifts that ground men down to old age at 40. It simply sits there, finished, safe, and utterly unable to convey what it cost to keep it running for the century it stayed alive. We look at a steel bridge today and see permanence, strength, the triumph of industrial engineering over raw nature. But that's only half the story. The other half is a converter floor in Braddock, Pennsylvania, where a brilliant engineer named Bill Jones, who'd spent his career trying to make this volcano survivable, was finally caught by it himself, and where thousands of men, whose names history never bothered to write down, stood in his place the very next morning. Because the steel still had to get made, the rails still had to get laid, and the volcano, whether anyone was ready for it or not, was going to erupt again in exactly 20 minutes. They don't make steel that way anymore. Not the machines, and not the men who stood close enough to run them.